In this tutorial, we'll take a look at the most difficult test as far as the circle is concerned, and that is the circle versus line intersection. First, I'm going to delete everything that we have created in our previous example, just except the one of the circles. So I'm going to leave the first circle and erase everything else from here. Again, we'll leave keyboard controls here for now because this is a placeholder, the clean slate starting point for developing a game or whatever JavaScript demo. And I'll refresh our view. And so let's also make sure that our sphere here is controlled by the mouse cursor by simply assigning mouse X and mouse Y. Again, this is from one of my previous tutorials. There's a mouse initializer here, and it's attached to the game, which is the canvas. So what happens is if we assign mouse X and mouse Y to any of our geometric shapes, they will follow that coordinate. And so I'll save this and refresh, and as you can see, we can drag the circle around with our mouse. I will also make the circle a little bigger, let's say 300 pixels radius, and refresh. And it's a little too big for our example. Well, maybe 100. Okay, this is good enough. And also, somewhere on the canvas, I'm going to draw a new segment. Let's say it's coming out from 100, and it goes maybe 400 pixels to the right and maybe 256 down. And let's draw this as a red line, 2 pixels, which is the thickness of this line. And let's refresh once again. So we have this line in this circle, and in this tutorial we're going to test whether this segment intersects with the sphere. And so the first idea of how to do that comes from intersecting the sphere and thinking, well, now we need 2 points of intersection, but we're not going to do that. And there's actually a more standard way of doing that, and that is by trying to figure out what the closest line is on the line to the center of the circle. So really there's only one intersection. And it makes sense because when you have such small distance between the 2 intersection points created by the sphere, really there comes a point where you realize that you only need one line. The closest point on this line, on the red line, will be indeed the only intersection point that we need to deal with. And what's interesting is this single point of intersection will be exactly the same point lying in the middle of those 2 intersections. It's possible to identify what that point is without calculating both intersection points. In order to demonstrate that and actually visually show the results, we first need to build a function that projects one vector onto another. But before we do that, I need to create that second vector that we will be projecting from, and let's call it segment 2, new segment. And it will also come out from 100 and 100, but this time it will be connected to the center of the circle. And so we need to take circle X minus 100 and circle 1 Y minus 100. 100 here and here are these values. So if they were 101, this one would be 101 too. And so now we can draw segment 2, 2 pixels in thickness, make it orange, and save and refresh. And this is the line that we were looking for. And so what we want to do is we want to project a vector, a perpendicular vector from orange line onto the red line, and we have to write the function in order to do that. And so let's go ahead and do that, and this function will go into our previously developed segment object, and so we'll be extending it to allow this new operation. And so we're going to type it somewhere here, and we want to project the vector onto another vector, and so this function will assume that this vector will be the first one, and the segment that is being passed into this function will be the one that we want to project onto. And actually, for that reason, we want to call it onto. And onto parameter will be passed as a segment, but we need to work with some of these values as vectors. And in order to convert onto, let's call it segment onto so that we don't forget. But the actual onto will be a new vector, and the vector class is here. And the main reason we're doing it this way is because right now in our library code, the vector is the only one that has cross and dot product, and so we will need dot product, and for that reason we're going to convert segments to a vector. That's easily done because remember, even our segments are defined as vectors, and something like this. And I'll define this vector in the same way. So this one should probably go here. And so now we have to do, remember that dot product, and so now we have to use the dot product, which is this function belonging to vector class, and it will return not a vector but just a value, which will be most likely a floating point, and let's call that value d. And let's take onto, and we actually need to calculate the dot product of onto itself, and that's just part of how this algorithm works. And if the dot product of itself is greater than 0, which can be depicted in this way, then we have to do additional calculations. Otherwise we have to return the 0 point. And let's go ahead and, before that happens, so in this case that there is no possibility that this calculation can take place, so we're returning 0.00. Now I'm not going to go into trigonometry or all of the detailed mathematical explanations behind this function. You can always look it up if you're really interested. There's YouTube tutorials, and just generally online you can find this out. But we're only interested in adding this function as in addition to all the others as part of our segment library. And I'm doing it this way because so we can actually start focusing on making the games rather than spend hours and hours on math and trigonometry. But this function is very important, and we simply need to have it as part of our library. And now we want to take the vector, which is this one that we created, and again we want to perform the same operation. Let's create a new variable and call it dp, and we'll take in vector and apply dot product again onto. This is the second time we're doing it. The first time we applied it onto with the dot product, and this time what we want to do in this case is create a new variable called multiplier, and the multiplier should be dp divided by d. It's just part of this algorithm, and the resulting points that we have here, let's say rx, will be equal to onto x. Remember, we calculated right here, onto x, and multiplied by multiplier, and our y will be onto y multiplied by multiplier. And so basically this is the way of casting a perpendicular vector, in other words, projecting one vector onto another. And we will simply return Rx and Ry as a point. And again, if this didn't happen, then we're simply returning 0, 0, which is not very useful, but we need to add that case as well. And so I think now it's time to go back to our game page and create a new segment, which this time will be segment 3. And the segment 3 will be segment 2 projected on to segment 1. And if we draw this segment right now, it's going to show up at 0, 0 coordinate system, which is upper left corner on canvas. What we need to do is we need to draw this on the orange line so that it casts down onto the red line. And in order to do that, we need to add basically a mouse cursor to it, which would be my guess. Let's try to do that. X would be mouse X, because that's where our sphere is. And segment 3, Y equals mouse Y. So let's go ahead and, having said this, recreate a... Actually, we're not doing this correctly. What we need to do is, I just remembered, the project function returns a point, not a segment. So let's make sure that this is a point. And now we need to create a new segment. Segment 3, new segment. And at this point, we will specify mouse X and mouse Y. And point 3 that was just returned should be the direction of that vector, point Y. So segment 3 then, if we draw this, it should draw the projection line. And I'll draw this in black and add 2 thickness. Hopefully this works. This is the first time I'm doing this, and in this tutorial. And let's see. Usually it doesn't work, but let's see what happens if we refresh the browser. And obviously it didn't fully work. There's a reason for that, but we'll figure it out. So the problem here really isn't that the algorithm isn't working, but we're not drawing it at the right time, in the right place. It should be actually be drawn at the center of that line. And let's save that and refresh. So now it's calculated correctly. As you can see, the black line will engulf the red line just close enough to be considered the intersection point. And so what do we do now? Now what needs to be done really is we need to cast another segment from the center of the circle onto this projection vector. You can see that projection vector is really like a shadow of the orange vector, and no matter where it moves, it kind of follows it as if there is a light being cast down on this vector. But that's why it's called a projection. It's kind of like casting its length, but only in one direction. And that's exactly what we need for this collision test. So now I'll go into the code and create segment 4. And using the segment object constructor, we're going to cast from, let's say, circle1.x, circle1.y, we're going to cast this segment onto, and the second point is a little tricky to determine because it involves multiple calculations, but it's basically, I would think that it's segment 3x plus segment 3 vector x and segment 3y plus segment 3 vector y. But there's one little addition that needs to be done. We need to subtract this circle from all that, and the same here. I do think that this is how this calculation is made, and just for clarity we'll put in parentheses, and let's see what happens when we draw segment 4, and I'll use green line to draw it, and 2 pixels in thickness. So let's refresh, and nothing is being drawn, but that's because I need to change this to 3 and not 4. And so we have the vector, but it's going in a different direction, and I think that's because we need to subtract circle from there, not to subtract from circle. I always get perplexed at some of these, and circle 1 y, and let's refresh the browser now, and as you can see we have calculated the green line, which is the vector that we were looking for. And now, just like in our previous tests, we need to determine whether the green line is shorter or longer than the radius of the circle. So let's go into the code and try to do that. And so all we have to do now is determine whether the segment 4, which is the green line here in the test, is longer, or in other words, if it's longer, there's no collision. If it's shorter than the radius, then there is a collision. And so if segment 4 length is shorter or equal to circle 1 radius line, it's, by the way, not the best name for this parameter, but just for this tutorial, then highlight circle. Let's draw this as red to indicate that there has been a collision. So let's refresh the browser, and so as soon as we get close enough, the sphere lights up in red, and it works on both sides. So whether you go like this or like this. And so basically this is the regular segment versus circle test. And one more thing that I will add just for fun is when there is a collision, I'll highlight segment 4 in yellow so we can actually visually see what it looks like when there's a collision. So interesting that it's drawing yellow. Okay, we need to add thickness, and let's refresh. And so here you see that this segment that we have been calculating for over 10 minutes or something is the key to this whole collision detection algorithm. If it's shorter than the radius, which is in blue, then there's a collision. If it's longer, then there's no collision. And that's basically how this algorithm works. Now there's one more thing that you might find interesting, and you can only see it if I decrease the radius of the circle, let's say 50, and let's make it smaller. Of course it still works, but if we go over the edge, you will see that it's still colliding even though it's going way off the edge of the line. And that is because this algorithm is tied to the 90-degree angle that's formed between the lines there. And it's really collision detection with a line that has no ending points, not just a segment. And for this reason, the sphere will collide even when it's outside of the line. So in order to handle that case, we first need to check whether the ending points of a line are found within the sphere. I'll give you another example by completely erasing the projected line so we can clearly see what's going on here. For example, we see that the ball is still colliding with the line even though it's totally outside of the line. The same works on this side. So we need to determine when the circle is actually within the actual line to prevent this algorithm from determining cases where the sphere is outside. In order to solve this problem, we need to take the original red vector, which is, let's see, the segment, the first original segment. We need to take the length of that red segment, and we need to compare if it's greater or equal to the length of the black projected vector. And let's get it back here. And so this was segment 3. Segment 3 length. This should help us further upgrade our collision detection algorithm for the case when the circle is outside of the line completely. And let me also remove the yellow orange line as well, just so we can see it clearly what's going on. And we'll refresh this here, and notice that it started to work. This additional if statement allows us to check whether the circle is completely outside. But notice that it does not work on this side. We still need to cover the case where this side works as well and the ball skips the line. We can accomplish that by making another test, but first we need to convert our segment to a vector, and we'll do it like this: a equals new vector. So we need to create a vector from segments vector direction. Vector y, and we need to convert also segment 3 vector to a vector b. Notice it's these exact same segment and segment 3 that we are converting to two vectors. The reason for this again is that only our vector type of objects in our library right now has the dot product function, and we can probably add dot product to our segment function, and that would make our job here a lot easier. But before that upgrade takes place for a segment library, we are limited to using the vectors dot product. And so in order to do this second test, we need to compare whether the dot product formed by the segment 3, actually this, I made a mistake here, segment 3, which is B, dot product of A. So if this condition is met, then there is still a collision. If not, then that collision is, the sphere is outside of the left hand side of the line. And let's save this and see if this actually works. Refresh. On this side it works just as before, And now it works on this side as well. So we have limited this test to the segment. But there's one more thing that we actually need to cover, because it works, but if you pay attention, when the actual edge of the line is not close enough to the center, this test is not going to work. This is just how it works. But there's a workaround for this, and it works for both edges of the line. And just know that there are actually two cases here at work. The first one is this, when we compare the yellow line with the radius, and if it works, there's a collision. And the second case, where we actually need to, in addition to that, test the line's edges against the circle. And let's go ahead and implement that as well. So we have a full circle versus line collision algorithm. Looking at our previously implemented circle, we see that we already have a function that returns true or false whether a point falls inside the sphere or not. So this is the function that we're going to use. And this should be the first step. Checking whether the edges of a line fall into the sphere should always be the first step. And if it fails, only then we start to proceed on to these other steps. If it succeeds, then we just end right there and treat this as a collision and never do any of these tests. So let's go ahead and see whether there's a point inside this circle, and that point should be the edges of the red line. And so the edges of the red line are, it's just a segment, so segment x plus segment vec x. Notice that we have to add segment origin to actual segment direction and length in this case, plus segment vec y. And so we're going to close this test. If there's a collision, then we'll simply paint the circle in red. And now in the same way, we need to create an else statement here, so we don't check more than once. And this test is for just the segment x, because that's the origin of the line. In other words, we first tested for the ending point. Now we're testing for the origin point. And we'll do it like that. And let's see if this works. I'll refresh the browser. And as you can see, once the point touches the sphere, it highlights it in red. Until then, it doesn't, and this works on both edges that we just added. And in addition, this test of course works. And so at this time, we have actually developed a complete test for sphere versus line intersection. And if you need to use this in your own games, simply download the source code that's available in this tutorial. It should be somewhere in the description or on the screen. So the source code already includes first this example and all of these libraries that we have developed, including keyboard, mouse, all of the collision detection so far that we have, circle, segment, vector, and point libraries. They're all there. So go ahead and download that, and I hope that this helps someone out there to progress on your quest to make video games. Thanks for watching, guys, and hopefully this clears a lot of fog. And this circle and line collision test is very important for many different types of games or whatever you want to do. Even physics engines sometimes use this this type of collisions, so you might start your own engine from here. And so thanks for watching, guys, and you can also support creation of independent video game tutorials by submitting a donation. You can just go to the link that you see on the screen, and I will see you in my next tutorial.